quantum mechanical model of the atom, chapter 7. So here again, chemistry is overlapping with physics. Until the beginning of the 20th century, Newtonian physics was pretty much all we knew about. And it was believed that all physical phenomena acted according to Newtonian laws of physics. And this is what governs objects that are large enough that we can see. So, they're giving you problems about things falling off mountains and cars traveling and things like this. That's Newtonian physics. And that is a deterministic view where what is happening right now with the object determines what it's going to do in the future. But around the turn of the 20th century, there were a number of physicists that discovered that for subatomic particles like electrons, what the electron is doing right now does not determine what it's going to do in the future. But you can't really predict. And here are some of the names of these guys. You've heard of Albert Einstein, I'm sure. Niels Bohr, de Broglie, Planck, Heisenberg. I actually haven't ever heard of that guy. It's nice that his name got stuck in there. I'm not sure how to pronounce it either. And Erwin Schrodinger. And these guys got into some crazy, crazy stuff when they were looking at these tiny little particles. So quantum mechanics, what is this? This is really the foundation of chemistry because it goes to what is going on inside the atom. Quantum mechanics explains the periodic table. It explains the behavior of elements when they bond together. It's the practical basis for all kinds of things, for lasers, for computers, almost anything technological that you can think of. Quantum mechanics is at the base of it. Quantum mechanics is a theory which explains stuff that's going on. So we need to understand what we're talking about here. Electrons are incredibly small. The word incredible means that you can't believe it, right? And they are incredibly small. If we think about this, a single speck of dust is very small, right? A single speck of dust has more electrons in it than the number of people who have ever lived on the earth in all of time. That's crazy, right? We just cannot even get our minds around how small an electron is. And the electrons are really what govern the behavior of most of matter. It's the electrons that cause the interactions between atoms of different elements and atoms of the same element. So it's the electrons that are really, really important. We cannot directly observe electrons. It's so small that observing it changes its behavior. And that's really a strange concept that we'll explore a little bit. Even with the most powerful scanning tunneling microscopes, we can only get very fuzzy pictures of atoms, and electrons are much, much smaller than atoms. So there's no way we can visualize them at all. And they are so small that if you do observe its behavior, that affects the behavior of the electron. So it's very strange. Even shining a light on the electron affects it. So we're going to watch a video. Actually, we're going to watch two videos about Schrodinger's cat. The link is there for the YouTube people. There's also another one that I like in conjunction with this. So if you go to my YouTube channel, well, actually, if you're watching this, you're on my YouTube channel. It's also in the playlist for this class. Okay, so we watched those videos about Schrodinger's thought experiment. And it's important to recognize the cat is a large object. The cat cannot be dead and alive at the same time. The cat follows Newtonian classic physics, the physics that I like and understand mostly. The particle, the radioactive particles that either decay or do not decay, are submicroscopic. And they are in this world of quantum mechanics. And they can be in this state of superposition, where they can be in two states at the same time. But we cannot observe them in both states. When they are observed, they have to be in one or the other. And that's the point of that thought experiment. And it was a thought experiment. No cats were harmed. Okay. So it demonstrates how quantum strangeness does not transfer to the macroscopic world. And if all of that doesn't make sense, or you feel like it's boggling your mind or making your brain hurt, you are not alone. These are some excellent quotes from these guys who were working on this. Niels Bohr said, "Anyone who is not shocked by quantum mechanics has not understood it. It is shocking. It is strange." Schrodinger wrote, "I don't like it, and I'm sorry I ever had anything to do with it." Okay? They're investigating particles, and what they're finding is very weird stuff. They're not liking it either, but it is what it is, and you can't make science behave the way you want it to behave. Albert Einstein attempted unsuccessfully to disprove quantum mechanics until he died. He didn't like it. He said, God does not play dice with the universe. You look in the bunker, and it's like rolling the dice, right? It's now either one or the other. You can't predict which. So very, very weird stuff. The good thing is we don't have to completely understand it in order to understand how it applies to chemistry. But this quantum mechanical model explains the manner in which electrons exist and how they behave in atoms. Newtonian physics does not explain this. It helps us to understand then and predict properties of atoms that are directly related to those electrons. And these are questions like this. Why are some elements metals and others are nonmetals? Well, it has to do with the electrons. Why do some elements gain one electron and form an anion and others gain two? It has to do with the electrons. Why are some elements very reactive and others are practically inert? They don't react at all. Why, in other periodic patterns, do we see what there's a typo in there. Why in other periodic patterns we see in the properties of the elements? Okay, that's so bad, I don't even know what it was supposed to say. So let's do this. It's probably hidden in your textbook somewhere.